what I want to talk about today is to give you a very broad overview of various applications all around the world that use for quantity and quality assessment. Okay, it's very, very broad, but if you have any specific questions, because almost each slide is a paper by itself, so I will try to go as detailed as possible, but if you have questions, please stop me and ask questions so that we can get into more details about how or what we did and why we did and things like that, or anything else you may have. And if time permits, I have another presentation. I will try to make that, and that is about the mismanagement of water resources in the Middle East. Right? So we'll talk about that, because right now, in the context of everything going on in the Middle East, that is another appropriate topic to discuss. Okay. So just to start off, I think yesterday you got a little bit about the background of the SWAT model itself actually, and it's been proven, meaning it's been applied many places for many applications, and we have more than 6,000 peer-reviewed applications and papers and things like that. And today I'm going to talk about a little bit about the continental scale or the country scale, and then worldwide applications. So yesterday I went through how the SWAT model works. So just to recap, we take the landscape and divide that into sub-watershed, and with the sub-watershed we overlay the land use and soil and soil plan to create hydrological response unit, the landscapes. So then all the simulations are done at the HRU. The outputs is sent to the river, and the river routing takes place. Okay, that's in a nutshell how the SWAT model works. Okay. You can set up your SWAT model in different configurations. For example, you can have a lumps model, just one subbasin, or you can have multiple subbasins with different HRUs. This is what the current SWAT does. Or you can go into the landscape unit, which is the next generation, the SWAT Plus, where you can take the watershed, divide it into subbasin, and then you can have a floodplain, upland, and the watershed divide. So you can have 3 or multiple zones, and within that each zone you can have HRUs. So it's a lot more detailed, more spatially explicit manner to capture the variability of land use, soils and slopes and things like that. Or you can set it up as a grid. Okay. So you can set up your model with the same data set. You can do it in any one of these configurations depending on your applications and how you want to model this watershed. Okay, what do we do in each HRU? The weather is a driving force, and that drives the hydrology, sedimentation, plant growth, nutrient, nitrogen and phosphorus, pesticides, land management, and bacteria. So these are all what we simulate in the model on a daily basis for each HRU. Okay. When you talk about land management, you can pretty much do most of the management actually, whether you are looking at the riparian, or whether you're looking at a deep tillage, okay, or if you're looking at the contour cultivation or strip cultivation, you can have stone bunds, okay, to protect the erosion from the slopes, okay, and you can look at things like pesticides or chemical applications, okay. So you can do pretty much all the different operations that you normally conduct in an agricultural rural watershed can be mimicked or can be incorporated in the model. Okay. Yesterday we saw the hydrology. Again, I don't want to go through in detail. For each HRU, you have a rainfall, and then that divides the landscape soils into up to 10 layers, and that rainfall is divided into runoff, infiltration. The infiltrated water can become evaporation and transpiration, and then any excess moisture here will come as a lateral flow back to the river, and again it can move to the shallow aquifer. From the shallow aquifer the water can return or re-evaporate. Okay? And eventually it can reach the groundwater. Each one has got its own time step. Okay? So it can be, some of them are hours, some of them are days, some of them are weeks or months, and some of them can be years. So it takes different time of travel to move the water from one process to another process. And once we finish the HRE process, we took the river process, where we look at the steady state along the longitudinal direction, meaning along the length of the river. It's a one-dimensional model, and it computes all the chemical process like dilution, diffusion, decomposition of your chemicals and things like that. This is just to recap what we discussed yesterday. Okay. So now, these are all some of the inputs that goes into the model, like your soils data, climate, precipitation, land use, land cover, topography, watershed and subbasin delineation. It's not an input, it takes from the topography and we delineate watershed. And the crop and land management, ponds, reservoirs, and best management practices or conservation practices, point source pollution, and atmospheric pollution. Okay. These are all the inputs. Not every input is required for every project. It depends on your project, depends on your watershed that you model. And these are all the different outputs that you'll get from the model. Okay. All the way from stream flow to sediment to nitrogen, different forms of nitrogen, different forms of phosphorus, ammonia, pesticides, different forms of biological matters like algae and chlorophyll, and then dissolved oxygen, bacteria, and metals. Okay. Again, just to give you more information, these are all the water budget. You can get the water budget. This is the sediment, nutrient and pesticide, and these are all the other outputs that you can get, like crop biomass, leaf area index, soil fertility, okay, and grazing management, okay, preferential grazing. All these different outputs can be obtained for the SWAT model, either at a daily or monthly scale or annual scale, by HRU, by subbasin, by wash. So SWAT is truly a spatial and temporal model, spatially distributed and temporally you can able to see how what's happening year after year after year. So I think I already mentioned we have just crossed 6,000 peer-reviewed papers, okay? And it is truly a global model. It's a public domain, open source. Anybody can use this model, and everybody will have access to the source code and everything. So let's jump into some of the national applications. Okay. So one of the projects that I will present this on Friday also. This is the national application where we are working with the US EPA, Environmental Protection Agency, to model the entire country, okay, on a cloud platform. And we are talking about exactly the same platform here in Brazil today actually. So we are talking to various researchers to see whether there could be a project or a proposal developed to CAPES or other funding agency to figure out whether we can develop a national model for Brazil. And this is quite successful, and we will help in that project actually. There is multi-million-dollar has gone into this project. So we have all the framework, everything already developed. All we need is just the data set from Brazil, and we can able to make this already. We have already done this on a prototype in Pernambuco state. So every watershed in the state of Pernambuco has been already modeled with SWAT, and that's available in this platform. So now anybody wants to model in the state of Pernambuco, they can able to use that cloud service or cloud platform to model this. So what is the real benefit of this HAWK system? It is National Watershed Water Quality Assessment System. It can support wide variety of application all the way from local scale, few hundred hectares or square kilometers, to all the way to thousands of square kilometers. Like if you want to model the entire Amazonia, you can model, or you can just model one small area within Amazonia basin. You can model that also. What are the main outputs? You know, sediment, nutrients, pesticides, and so on. The same usual SWOT outputs. In the US, we divide our watershed into hierarchical system or hydrologic unit code, HUC, not the HRU, HUC. So if you look at typically, if this is one HUC, that's further divided into sub-basin, that's further subdivided into even sub-basin, and then finally the smallest. So we have all the way from 2-digit is like entire Amazonia basin. Okay. Then 4-digit, 4 unique ID number. So you have a watershed ID, just like we all have an ID, national ID system. We have a watershed ID system for the entire country. So we have 2, 4, 6, 8, 10, 12, 14. So 14 digit means smallest area is about 15 square kilometer. So if you keep on adding every 15 square kilometer, you can make the whole country. So that's what basically this whole system. So you don't have to come and delineate watershed. We already predefined all the watersheds for you. What are some other benefits? It's using public domain databases, tools and technologies, so you don't have to develop your own inputs. All the inputs are already pre-processed. You don't have to go and look for soils. You don't have to look for land use. You don't have to look for weather data set. All this being already processed based on the best available data at the time of creating that project. We can always come back and update that actually. Let's say 5 years from now you have more weather data, you add more weather data. 5 years from now, you have better land use map, you add the better land use map. You don't need to know any GIS skills. Everything is cloud-based. Okay? You don't need any software. It's all using just web browser. You don't have to install anything on your local computer. Everything is running on the cloud platform. You can do a standard assessment, meaning just clicking and running the model. Or you can also download this onto your desktop and run more detailed analysis. So it has got both online and offline capabilities to develop this model. You can perform post-complex analysis to very simple analysis. And then the most important thing is it can reduce almost 90 to 95% of the time it takes to set up a model. Today, those who have put together the data set by hand, I know Mariana and others have done it, it takes a lot of time, especially in soil state. Okay? It's not well established, and MPAPA has not put together a national database yet. Okay? So every time you want to run a model for your watershed, you have to develop all the inputs required. That takes a lot of time. With this being processed for the entire country, it should not take you more than over 5 minutes to set up any watershed anywhere in Brazil. Don't you have to set up like that? That's what we do in the US. You can now run the model under 5 minutes to any watershed in the US.
We lost more time getting the data than calibrating.
Yep, exactly, you're right. That's the main idea here actually. Because every time there is a master's student or a bachelor student or a PhD student want to model a watershed, they have to go through the same process of collecting data, preparing data set, and making sure all the databases is correct, and go through the software, knowing the GIS knowledge and experience, putting the data set. So they spend almost 6 months to do all this process. Then they'll have only 2 weeks to run the model, evaluate the model, and write an application or thesis or master's or PhD and things like that. By having this, you eliminate all this process so the students can spend more time on applications and developing products rather than worrying about input data. I'm not saying this is perfect system, but this is perfect for many applications. Not everybody is expert in hydrology. Not everybody is expert in water quality. Okay. So if you have a national modeling system that is somewhat calibrated, then you don't need that expert anymore actually. So people ask me when I develop this stuff, they ask me why am I shooting myself in the foot actually, meaning I'm putting out of business myself. They don't need me anymore at that point. I would say that's the best day for me actually. If nobody needs me, I'm done the job actually. I can go home. But the main idea here is to have the non-engineers, non-hydrologists to use our models, meaning the economists, the environmentalists, the ecologists, okay? So the policy analysis people actually. So management. So if they want to use this model, they can be an expert in SWAT to apply the SWAT model. Okay. That's the main idea here, to make this tool available openly. Again, this is again open. Anybody can use the system anywhere in the world. And we have already implemented in entire country of India. The Indian government has adopted it. And now we have the entire country of Poland, Ethiopia, and so a few other countries have already adopted this as a thing, as a modeling system. And we are working on more and more. Like right now, I'm working with South Africa, for example. Okay. And I'm hoping one day we will have one in Portugal also. So that's the idea here. So I think all the thing what I said is already here, kind of. So automated data processing, internet-based. So you can even do it from your phone. You don't need even a computer. All you need is internet access to any browser. It's one of the most efficient, non-modelers, like as I mentioned, ecologists, environmentalists, all can use this. You can have multiple users. This is one of the key thing actually. So right now, for example, if you develop a model on your desktop, if you want to share that model, you have to literally take the model out of your computer and send it to somebody else actually. By having this, you don't have to. Everything is online platform. So with the click of a mouse, you can say, I want to share this model with Mariana or with someone else. So whoever you want to share with, you can just send them the email, then they will have automatic access to that model. Okay? They don't need to come and download the model or ship the model and things like that. They will have instantaneous access. So you may be a hydrologist, somebody else may be a groundwater specialist, somebody else may be a water quality specialist, somebody may be an agricultural specialist. All of them can work on the same model over the cloud. Okay. And another beauty is, most of the time what we have found is the institutional memory. What I mean by that is, if somebody, an expert, who is working in a particular area, when that person retires, or when that person leaves the job, all the things what they did is also gone. There's nobody there in the institution to capture all of them and archive it and make it available to the next worker or the next follower and things of that nature. By having this, you are creating a living model that's going to be online, so that even if they leave, all the systems are there. You can easily reassign all of them to whoever is the next person who is going to take the job. Okay. So you don't have to recreate the same model over and over again. Suppose if I created a model for a watershed here, and 5 years from now I want to come back and re-look at that output because the land use has changed significantly, or the forest has deforested, I can come and run another analysis very quickly. I don't have to go back and recreate all my model from scratch, because already I have a calibrated model. It's all going to be online. Even if you are not doing it, maybe somebody else in your organization wants to do it. So that's the beauty of this system. Yeah. Yeah. That's what we do. So it's not only that you can share the model and you can develop the model and you can keep the modeling on system, but you can also share your model from your desktop to the cloud. If you develop your own model on your desktop, that's much better model than what the cloud is offering you. You can upload it and share it with everybody. Okay. So you can share it with everybody, or you can share it with only few, or you don't have to share it with anybody, just keep it to yourself. We are not going to tell what you need to do. We are making this platform available, that way you can do anything you want to do with the platform, with the data, with that model. Does that make sense? So some of the analysis you can do with Hawks is you can look at the different management, changing land use, different fertilization rate, different animal operations, or you can do different pollution control scenarios, both point and non-point source or atmospheric sources, or you can also evaluate climate change aspects. Okay? And you can also look at the environmental benefits and conservation practices at national to regional scales. So that's where we started, and this is just an example of one output product. This shows you the nationwide stream flow. Okay. So how much rainfall runoff generation? Okay. Or how much is the sediment from each HRU to the nearest river?
The red ones at
The high value.
heights.
Yeah. The reds are the high and the blue are, the green are the lowest. Here is for the nitrogen and phosphorus. Okay. So there's no surprise that all this area is all red. That's because this is the major agricultural production. The Mississippi River Basin. Okay. That's why they are all highly red in color. Then we also did an analysis on, again, like I said, each slide is a paper by itself, so I can definitely share the papers if you're interested in. So this is to look at the El Nino and La Nina effect on climate, on agriculture, or in water sources. Okay. This shows you change in water yield. Red means less, dark pink or magenta color means more. Okay. So the yellow is kind of neutral. What year? No, this is for taking all the El Nino years in the past and analyzing it to show you how much water is available during the winter, spring, fall, and summer. Okay, so you can see the focus on the red. So you can see the red means there's less water here, as much as 50% less water. Okay, in the west coast, for example. And in the summertime, it's in the Midwest here. Is the map. So, because each region is different production zone. Okay, so the water availability is going to affect how much is going to be available. The same thing for the fall. Fall means snow. You're going to have less snow during the time. Okay, so this is on neutral El Nino, right? Let's look at the strong El Nino. Strong El Nino means you've got very strong signals, you're getting more rain. Okay, so this is where the more rain actually. So you can see these are all going to be getting flooded. This area will be all flooded actually. That's a very dark color here. They are all flooding happening under strong El Nino conditions. What happens? What happens? If you look at the La Nina, which is the dry period, okay? If you look at the La Nina conditions, and this is what happens here actually, so you still have some strong signals in certain packets actually, like in the spring in the northwest. But if you look at the consistently, the California is all dry throughout the year in the La Nina period. And as you know, California produces all the vegetables and fruits for the whole US. So that will have a significant impact in terms of agricultural production during the La Nina period. Okay. So this year we are expecting one of those years. The coming year is going to be La Nina year because of the Southern Oscillation Index in Australia. The temperature is very, very warm. The sea temperature is warm. So we are going to have very mild winter, meaning your winter won't be as cool as we normally have. It's going to be hot when it's a mild, it's above normal temperatures. We also looked at the climate change applications in terms of yield. This is wheat. Okay, yeah.
Sorry.
Sure, no,
I didn't understand which data do you use to
But
for those movements.
Yeah, so what we do is we took the 30 years, right? out of the 30 years, we take all the La Nina years, okay, and then do the analysis just for the La Nina years. And the same way we took the strong El Nino years and we did the analysis for that as well. It's not a mean, it's whatever the real data that year, okay. So if you have out of 30 years, let's say 5 years is La Nina year, we take those 5 years data and then run the simulation and look at what happens. This is the average of the 5 year. Average of the 5 year La Nina year period. So this is looking at the wheat yield actually. As you know, most of the wheats are grown in this region. Okay. So this is under current condition actually. This is the baseline. Under current condition, the typical yield will be somewhere between 3 and 5 tons. Okay, so this is the wheat yield. If you keep the carbon dioxide level at the same, but year 2030 and year 2095, okay, this is the future climate change projection based on the temperature and precipitation change in the future. Okay, so what we are showing you is if the yield from the baseline is negative, meaning less yield, that will be in dark color like red color. If it is positive, it's going to be in blue color. Okay. So you can see under 2030 at the same carbon dioxide level, most of them are going to be negative on the western side and it's positive on the eastern side. Okay. This is for wheat. SWAT can also handle the change in carbon dioxide. Okay. So you can change the level of carbon dioxide. If you recall, the carbon dioxide level was about 270 or 300 parts per million. Today we are close to 450. Okay. So the projection for the next 100 years is going to be somewhere between 600, 450, 600 or 700 parts per million in the next 100 years. So if that is the case, if you are going to increase your carbon dioxide level, you can see everything turns to more positive. The yield is going to be more positive, meaning yield is going to increase by 1 ton or 2 tons per hectare. So for agricultural community, carbon dioxide is good. Okay. The more the carbon dioxide, the better the plant growth, less water is required. You don't need the same. For the same amount of water, you can produce more with higher carbon dioxide level. Okay. But it is not a linear. It will go up to a certain level and it will become flat. Okay. It's not going to keep on increasing the yield forever. So carbon dioxide is good for agricultural community in that regard actually. So again, the kind of analysis that you can do with SWAT, here's like another example on the climate change. Then we started looking at the global applications. So one of the papers that was published in 2002, okay, by Yang and her group developed a paper that showed the virtual water trade. What do you mean by that? Means when you are importing or exporting, what are you importing and exporting actually? You are importing grain or exporting a grain. Okay? So for example, Brazil may export sugar cane or sugar, or petrol, right? That's sugar, that's sugar cane, right? So what are you exporting? You are actually exporting what? Clean water. So you are going to keep all the pollution in the country and exporting the clean water. So that's what this group analyzed. For every country, each dot represents a country. Okay, this is representing 1980 and this represents 1990. So if you look at it here, the x-axis is how much water consumed by person per year. And this is the net cereal input. Cereal means anything, it can be any grain. It can be corn, it can be wheat, it can be sugarcane, soybean, whatever they are exporting. So if you look at it here, the first in the most left-hand side, these are all Middle Eastern countries or dry desert countries. Okay? If you look at Israel, for example, the water availability is less than 500 million cubic per water, and their import is significantly increased during that period. Okay? So no country or no year shows from going from this direction. Everything is going in this direction. Okay? So that means less water per person, more population, and more import. Okay? Obviously, the production technology has improved. Previously, what used to produce in the same land, now we are producing 4 times more. Okay? Production has increased, but the net import is what we are talking about. When you are importing clean water. Whoever is exporting is sending the clean water, and they are keeping all the environmental problems locally there. So this started us thinking about doing some global modeling to look at what's happening, where the water pollution and water transfers are happening. So you don't have to literally, because it's a lot expensive to transport water from one area to another area, right? You can put it in container. Oil, yeah, you can, because oil is more expensive, but we don't value water, right? But you can convert it into grain and then ship the grain. That means you are shipping a lot of water, because you know how much water it takes to grow grain, right? An average about half a meter of water, 500 to 600 millimeter of water is required to grow 1 kilogram of grain. So that much water is required means you can see based on the amount of export how many billions of gallons of water we are exporting. Does it make sense? In concept? Yeah, sure. Yeah. So this is where we use the SWAT model to analyze the blue and green water. Okay. What is the blue water? Blue water is nothing but your stream flow, lateral flow, return flow, groundwater recharge. So this is the renewable water. This is the water that you have access to. When there is rain, this much of the rain is typically available as a renewable water. This is typically somewhere around 10 to 20%, depending on where you are. Okay. In the Amazonia basin, it could be as much as 50%. Okay. In the northeast Brazil, it could be only 5%. Because it's very dry, humid, more evaporation, less rainfall. Okay. Then, this is the evapotranspiration, is the green water flow. This is the amount of water that goes back to the atmosphere and consumed by the plant. And this is the green water storage, how much water is stored in your soil and below the soil. Okay. So if you want to increase blue water, if you think you want a better blue water, then you have to decrease production. Okay. Agricultural consumption or plant consumption. That's the only way. I mean, this is fixed. This is a water balance actually. We can't create water. Water cannot be created actually. It can be manufactured. So only based on what's available. This is what's coming in, and these are all what's going out. So it's very simple equation. Precipitation is equal to ET plus stream flow and groundwater. So we started looking at this concept with Africa, for example. We simulated the entire Africa, and we're looking at the blue water. This is how much blue water available in Africa. Okay. So this is how many millimeter per year. This is an extremely dry region, so there's hardly any water, any rainfall. So most of the water is in this region, western part of the Africa and a little bit of the eastern part of Africa. This is the Blue Nile. This is Ethiopia. That's where the Blue Nile starts. That's the White Nile and Blue Nile. That's what flows. Right? And this is the green water flow. How much is evapotranspiration? on the plant community. So the sum of these two is going to be your precipitation. So what's surprising was South Africa. Look at how dry it is actually. I don't know whether you saw the newspapers about a few years ago. The major metropolitan city is ran out of water completely. Okay? So they cannot even supply water to the citizens for more than a few months until the next rain came. Okay? So it's an extremely difficult situation in South Africa. Okay? So that's what you're seeing here in this map also. This is the average of 30 years of simulation. So these are all very nice models. What do you do with that model actually? You can run a lot of scenarios looking at the water and food security, the virtual water flow. Remember the one I talked to you about how import, export, and we can look at those analysis. We did a lot of climate change analysis and scenario analysis to see what we can do. Okay. Then we looked at, based on the FAO, Food and Agricultural Organization, they say if you have at least 500 meter cube to 1000 meter cube, that's the minimum requirement of meter cube of water per person per year. Okay. So we overlaid the population on our blue water and looked at what are the areas where we are able to meet the demand. I know, as you know, Africa is not densely populated. Of course, we have a lot of animals, maybe. We did not take into account that water requirement for animals here, or wildlife. It's strictly looking at population. So if you look at that, actually, again, there are packets that we are not able to meet the water demand based on the population in that region. Okay? So you can see in the South Africa has got more of those. So you can perform analysis like this with SWAT. And this shows you from every country in Africa how much blue water in millimeter per year is available. So some other country like this has got, Senegal has got the most water. There are other regions like in Algeria and few other northern countries has got the least amount of water. So this gives you a national picture, and this is model simulated, and this is the FAO estimate. So you can kind of get an idea that there is a general agreement between, FAO has got few data points, whereas we model every land and soil in the watershed. Okay. So we have general agreement between the FAO numbers and the SWAT numbers. The SWAT is a range, that's because it's a 30-year. That shows the range of over a 30-year period. Okay. One of the worst year you could be here, one of the best year you could be here. That makes sense? We have published about 4 papers from this work actually by a PhD student, so we can get you a copy or it's available on the SWAT website. When we talk about climate change, one of the challenges we have is agreement between models, because there are lots of climate change models. Every country has got their own climate change models, right? Right, which one is producing the right information? So we did an analysis in Africa of all the 36 different models, and you can see how many different models have an agreement at least 1%, within 1%. Okay, in these. None of the models, the red that you see here, there is no model has an agreement on what's going to happen in the future. Okay? There are between 1 and 6 models have agreed what's going to happen there. They are within 1% difference between the projections of future precipitation. And if you look at the upside, if you look at the blue, which is 13 to 18, so these are the places where there is the most agreement on what's going to happen in the future. So the polygon that you see here is a sub-watershed that we see there. Okay. So in each sub-watershed, we looked at what is the agreement across all the climate change models, how good the future projections will be in terms of precipitation, whether it's increasing or decreasing, doesn't matter. Do they all agree with each other or how different they are? And then we simulated the climate change, and this shows you the baseline. This is the today's condition, okay? And this shows you the percentage difference with the future climate change. Darker the color, the dark red means more dry. The blue means wet. You may wonder why there is more wet in the desert actually, because in desert only the rainfall is only about 50 millimeters for the whole year. That's equal to 1 day of rainfall per year here, right? So if they increase it by 25 millimeters, that's almost 200% or 100% more. So don't fool by this. This is percentage of change, not absolute number. Okay? And this is the coefficient of variance. But what is the variance in that number? Like if you're looking at 30 years, what is the variance over 30 years? The output from SWAT you can also use to look for things like floods or droughts, the frequency of flood, frequency of drought. Because when you look at the risk assessment, you need two things. One is the duration and the intensity. So if you multiply intensity times duration, that is your risk. What is the intensity? Intensity means severity. How severe is the drought? Okay. Drought and flood are relative phenomena. What is drought for somebody may not be drought for somebody else. Okay. So it's difficult to measure. But the duration of the drought, how long the drought is important. Because when you talk about flood may go on for maybe a few days to weeks, 10 days maybe. But drought can be for years. And most of the time, you don't know you are in a drought until you are in a drought. It's very difficult to find it, just like a recession, right? You don't know you are in a recession, economic recession, until you got into a recession, actually, until things get really bad. Whereas on the flood, it's going to happen one day, or a few days, or maybe a week or 10 days to maximum. So with the analysis, we are able to show the historic, the past 20 years and the future 20 years, where the drought or number of years are. This is the length, number of days. This is the number of drought period actually. So you can see there are more droughts are expected in this region here. In this region in the future, based on the climate change projection. I'm not saying this is accurate or inaccurate, based on what are the projections that we had at that time. Okay? Any questions on that application on the international? Yes?
To clarify, you can show the difference in the simple water balance with this method.
Yeah. Because you cannot manufacture water, right? Water is what's available based on rainfall. You can't create water. It's not like something you can go on plastic, let's say. You can create plastic, but you can't create water. So another application on the virtual water trade we did for the entire country of Iran. Okay, as you know, Iran is being isolated for more than 25, 30 years now. So for more than 30 years, they can't import, export. Okay, they have to produce all the food for themselves internally because of the embargo and because of all the geopolitical issues they have, right? So we looked at the virtual water trade strategy, and how bad or how good it is. So we divided, this is the country of Iran, surrounded by Afghanistan here, Pakistan here, Persian Gulf, Iraq, Turkey, Syria, and so on. So we divided the watersheds into 8 regions, 8 major river basins, and we modeled every one of them actually, and we have a calibrated model. And this shows you how much is the precipitation, how much is the blue water, the green water flow, and the green water storage. Okay. So you can see, if you look at the right at the center, if you draw a line right here, the east of this is all completely desert. Okay. The average rainfall is only 40 to 100 millimeters. Okay. It's completely desert. The west is all the mountains, and that's where the snow, and that's where most of the rain happens. So this shows you by this shows you the rain-fed yield. Yield means the main production in Iran is wheat. They grow wheat because the rain season is winter. So they have to grow wheat to produce. You can't grow corn during the winter time. Okay? So rain-fed yield for wheat is what you see here by year. You can see there's a lot of variability. That's because rainfall is variable. Okay? So how many tons per hectare it produced? And then if you want to look at that same thing, how much, this is by province or political boundary. Okay? How much water the green water flow, how much water they consume. Okay? Somewhere between 800 millimeters on an average. Okay? If you do the irrigation, instead of rainfed, if you put irrigation, your yield sometimes even less than the rainfed yield actually, but it's a constant because you are able to supply the water, right? There is no variability in rainfall here. Okay. But what we are really interested in is crop water productivity. CWP means crop water productivity. For every meter cube of water, how many kilograms of grain you can produce? Okay, this is the kilograms of grain per meter cube of water, and this is the each province. Okay, so you can see some of them can produce very efficiently up to 0.6 or 0.8 kilograms per meter cube of water. Others can only produce 0.2 or 0.3. So when you talk about virtual water trade, you are moving water within the country from one place to another place to irrigate to get crops in order to produce self-sustained, because they can't import grain. They have to produce what they have to eat inside the country. Okay. So this is what's happening, and then we did a few analysis such as what happens if you are able to increase the irrigation efficiency. Right now these infrastructures are all 40, 50 years old and is very in poor shape in terms of management and maintenance of the irrigation structures. So we looked at it, what are the areas it makes sense to produce, to fix irrigation system and produce more yield at the same time. You don't want to put investment in areas where the yield is already very poor. Okay. So we looked at what are the different regions where you could potentially improve the irrigation efficiency and produce more. Okay. And definitely you don't want to invest in these regions. Very poor yield, very poor irrigation structures, and so on. Okay. And you can also look at the same thing in a different ways, ET versus water availability. Okay. That's another way of looking at that. So we're trying to do a country level analysis on water resources. What are the different projects that is economically feasible, environmentally feasible, and also makes sense actually. Just because you have water, that doesn't mean you want to transport all the water from west to the east to grow in the high temperature desert actually. That's what they're doing right now. So what they're doing is they are taking water from the west and moving all the water to the east. Remember, yeast has got a completely dry area to produce wheat. Okay? And that's what we are showing you. The crop water productivity on this side is pretty decent, and as you go to the east, it's very poor. Any questions so far on the Iran application?
Yeah.
Yeah, go ahead. Yeah.
What about SWAT for tank cisterns? For example, in northeast Brazil, we have probably maybe the most the semi-arid with the most precipitation in the world. So we have a system of cisterns of tanks.
Yeah.
Does SWAT help to
Yes.
build this kind of system?
Yes. We have used we call it as ponds, tanks. They're all very similar. So you can analyze the ponds for two reasons. One is a lot of these ponds were constructed 50 years ago, right? Today they are all silting up, meaning erosion from the landscape is filling those tanks. Okay? So if you don't revive that tank, then you're not going to have water storage for either municipal water use or for irrigation downstream. Okay. So we have analyzed using SWAT, looking at the amount of sedimentation, siltation going into those tanks. And the next question would be, where else can you put a new tank? Okay. So you can be able to analyze the flow and the sediment coming through the river to figure out what is the next logical place to put a tank. Okay. So one of the, if you look at, for example, Texas, it doesn't have any snow. In the north, it's all snow driven actually. Okay, you have a land that can store water during the winter months, right? Whereas in Texas, there's nothing. So we have to have big lakes to supply water. Those big lakes is expected to have a lifespan of 100 to 150 years. To protect that lake, you put the ponds upstream, so that those sediment, before it goes to the big lake, it gets stored in those small tanks, and you can easily remove those sediment from the tank and keep reviving it and things like that. So again, we use SWAT to look at those impacts like that. Any other questions? Okay. So this is another part. I showed you some in Africa, then one in Iran. Now we are looking at Southeast Asia. Okay. So the Mekong River Basin is one of the good example of how they use model to look at the water resources and sharing of water resources within the country. Okay. Is there time for a break time? No, right?
Maybe 15 minutes?
15 minutes?
Or now?
Okay, that's fine. So Mekong is divided into Upper Mekong and Lower Mekong. Upper Mekong is 100% in China. Okay. So Upper Mekong is starting from here all the way up to here is Upper Mekong. So this is all in China, a little bit of Myanmar or Burma. Okay. The Lower Mekong is Laos, Cambodia, Thailand, and Vietnam. 4 countries. So a total of 6 countries share the water resources. The problem is the Upper Mekong River Basin, this is all completely hilly area, mountains, right? They have built massive dams in those mountains. So if China decides to open the gate, it can flood everybody here. Okay. So that is a major challenge. Okay. So if there is a dam break or there's something happens there, because nobody lives here actually. There's no humans are living in this region because it's extremely cold and it's high in the mountains. We are talking about 8,000 meters above sea level. Okay. This is the Tibet plateau that we are talking about. So, and if you had more snow, this spring you are going to get more water, that they are going to open the gate and it's going to flood downstream. So there's no real control on the Upper Mekong Basin. So the Lower Mekong Basin which has got more area, almost 77% of the land is in the lower Mekong. Okay. Of that, Cambodia, the whole country of Cambodia, 86% of the Cambodia is in one river. Okay. And the Laos has got 90% of the land is in one river basin, which is the Mekong. Thailand has got 37% and Vietnam is about 20%. So what are they doing with that actually? They are trying to look at how the change in management by China is going to impact the lower countries. So they are looking at all the major dams in China using SWAT. They are also looking at the small and medium dams like hydropower dams, irrigation dams in Laos and Cambodia. And then irrigation development, forest cover reduction, meaning removing forests to do agriculture and things of that nature. Freshwater fisheries. One thing about this river is 6 months out of the year, the water flows from north to the south. The remaining 6 months, the water goes from south to the north. This is the only river in the world where the water will reverse because your elevation is lower during low flow. Okay? So the sea level is higher. So the sea water will go back into the country actually. It can go all the way to 200 to 300 kilometers into the country. So in Vietnam, during the rainy season, they have fresh water and they use the fresh water to do the fisheries. During the the low season, the water goes, so they use the salt water to do the fisheries. Okay. That's what the brackish water. Brackish water means water from the sea going back into the country. And then the high population. Population on this region is exploding like anything actually because they are all were under dictatorship until very recently. Okay, Laos and Cambodia especially, near Vietnam. So they are all coming out of that. The population is more free to move around and resettle and things like that. So that's causing a lot of concern. So again, SWAT is the preferred model by all the countries. They are using just one modeling system so that everything is open source, so everybody knows what exactly is happening and they are able to share how much water is available. So any new project, all country has to approve. They can't just unilaterally China cannot do what China is doing actually. So all the countries are now sharing the information and they are using the SWAT model for all their applications. Okay. Just one slide, but after that we'll take a break. This is another project in Kenya. So this is the same thing going back to your question. This particular dam was constructed by UK, England, for Kenya, and the lifespan for this is supposed to be 100 years. Okay. But this is the actual color of the water. It's not colored actually, it's actual color of the water. This is the dam that produces electricity and drinking water supply to Nairobi, the capital city. The poor land management, they converted all the forest here into tea production. Okay? So because of that, now completely all the land is eroded and that's all gets silted up here. So the recent survey they did, they're looking at now 50 to 60 years, only the lifetime of the dam. Because building a dam is not cheap or not easy actually. So what used to be 100 years dam, now it can have only 60 years because of the poor land management in the upper. So this is the Mount Kenya, and all this area they removed the forest and put tea here. Okay. So we ran some simulation by reforesting, removing those trees and putting forest back at about 2,000 meter elevation, 1950, 1900, 1850, and we came up with how you can reduce the amount of erosion going into the lake. So this shows you if you are able to do that, you are able to extend the lifespan of your dam. Okay. So this is the percent of sediment reduction. how much you can reduce. You can reduce as much as 10% if you are able to increase your reforestation about 1850 meters elevation. Any questions so far? So the next set of slides is to talk about water quality. I talked about a lot about water quantity, and now I want to talk about water quality here actually. And this is a watershed in Texas. Okay, it's called Cedar Creek watershed, and this Cedar Creek watershed supplies water to the Dallas area in Texas for about 4 million people every day. Okay? So this is the main water supply reservoir. And to protect the quality of the water in the reservoir, they are using SWAT model for that. Okay? So what is the best effective conservation practices that you can put to reduce the total phosphorus in the lake? Because right now the lake is creating a lot of green algae, and every day the water treatment plant has to treat that water before they can supply to the house, the tap. Okay, they are spending about $1 million a day to clean the water. Okay. So one of the questions the managers of this water supply reservoir is asking us, where is this phosphorus is coming from in the watershed, and what they can do to remove the phosphorus or reduce the phosphorus going into the lake. Okay, so this is the lake. They manage 5 lakes, 1, 2, 3, 4, and 5 lakes. The watershed that I'm talking about today is just this watershed here, Cedar Creek, and they supply the water for the entire city of Dallas and Fort Worth. Okay. So this gives you a perspective, chlorophyll. This is the algae in the lake. You can see from 1989 to 2006, you can see there's a steady increase of algal grade. It's almost 4% per year is increasing because of phosphorus load going into the lake. Okay. So we developed a framework where we took all the GIS data, developed a SWAT model, calibrated that model, and then we have various water treatment plants in the watershed, but also we have the lake model actually, because SWAT is weak in water quality for the lake. So we use another model called WAS. Okay, it's again a public domain model. That model can handle the 3 dimensions of the lake, both space and vertical. Okay, so we use this model here, and we also engage the stakeholders, meaning the farmers, the producers, the industry, the city. They all got involved here, and then we applied an economic model to select the best management practices to reduce the phosphorus pollution. Okay, because we want to make sure what is best possible, whether we can reverse the trend of increase in algal production. So there is some amount of reverse modeling. This is done in this analysis. So if you look at in this watershed, the total amount of nitrogen is mostly coming from grassland. Okay. So if you look at it, let me show. I think the scale is not shown here. Actually, I mean so if you look at it here, there is 6% of the agricultural land that produces almost 12%, whereas 35% is coming from grassland. Okay. So one of the things that we need to target is, when you're doing the conservation practices, which land use to target to reduce the pollution coming from that land. Okay. And then this is the grazing land animal operation. Almost 50% of the nitrogen is coming from animal operation. But the problem is nitrogen is not limiting. It is the phosphorus that is creating the algal flow. We have excess phosphorus. Remember yesterday I mentioned to you, every 1 kilogram of phosphorus you need 8 kilograms of nitrogen. Okay. So in this particular case we have more phosphorus than the nitrogen going into the lake. So this is the baseline. Based on a 37 years modeling, the annual load of sediment is about 450,000 tons of sediment going into this lake. Of that, 1.5 million kilograms is nitrogen and 188,000 kilograms is phosphorus. So they have to reduce this phosphorus by 35%. This is where we did a reverse modeling, going back to the lake model and look at it, how much we have to reduce to reverse the trend of the algal production in the lake. So that means we have to reduce this load by 35%, meaning from 200,000 we have to bring that down to more like 150, 140. Almost 60 to 70,000 kilograms we have to reduce. Okay. So that's the objective for this project. How do you go about reducing the phosphorus production? Okay. So we chose based on the economic analysis and environmental analysis, we chose these practices like filter strips, putting grass next to the agricultural land so that the runoff from agricultural land is getting stored in the grassland before it goes to the river, for example. Okay, that's filter strips. Grade stabilization, removing the slopy land actually and making it a little more flatter. Okay, grass waterways, growing more grasses in the channel so that you can reduce the velocity of the water. Okay, and then terraces. Wherever there is a more than 2% slope, we want to put steps. Okay, so terraces. Conservation, converting the cropland to grassland, because 6% of the grassland produces almost 24% of the phosphorus loading. So we need to reduce the amount of cropland. So convert the cropland to grasses. Okay. And then finally, prescribed grazing. That means do not overgraze. So don't allow the animals to eat the grass too much. So we have to keep the amount of grass on the land more in order to reduce the sediment and phosphorus. So these are all the different parameters we have to modify in the model to account for these practices. Okay. So the first thing we did was we went and said, what happens if 100% of the farmers accepted the challenge and willing to work with us? If everybody does the job right, what will happen? So if 100% of the farmers put filter strips, that can reduce phosphorus by 30%. Okay. If 100% put grade stabilization structure, that's going to only produce 2%. Okay. And grass waterways, maybe another 2%. This conversion of grassland to pasture land is going to reduce as much as 35%. Our goal is 35% reduction in phosphorus. But we can't expect 100% of the farmers to cooperate, right? Everybody cannot cooperate. So we have to do some optimization. So we took these numbers and gave it to the economists. Economists ran an optimization model based on how much it's going to cost to do this conversion. Who's going to pay for it, right? So they did an economic analysis and they came back and said they wanted to put 50% on filter strips, 100% on grade stabilization, 20% on critical pasture planting, terraces 15%, wastewater treatment conversion of grassland to agricultural land to grassland is 20%. So they came with a combination of all the practices with the different thresholds, okay, based on the cost and the adoption rate, because they did a survey with the farmers to see how many of you are willing to do the changes. Okay. So it took a lot of effort in coming up with this data, sorry. But I'm going forward, okay, I should go back. Yeah. Okay. So we took this information and then we went back to the model, and our target is to reduce to 35%. So this is the baseline phosphorus loading from the watershed. How much phosphorus is coming? So this gives you how many kilograms per hectare. The green, light green means less, dark red means more. Okay, more phosphorus. So we applied, we ran the SWAT model first, look at the total phosphorus loading. We did the ranking of which sub-basin produced the most, and then we applied the BMP based on the economic analysis, and then we go back to the model run. So we did it iteratively. Okay. We went back and forth on this over and over again until we reached the 35% goal production goal. So if you just look at it, this is the baseline, okay, from the landscape, and this is what's happening in the river. So taking the baseline, first we adapted the filter strips. Filter strips gives the cropland. This is the area that's grown with grassland to protect any runoff, direct runoff from the grassland to the from the cropland to the grass before it goes to the river. Okay, so we adapted that. So this is it converted some of them actually. Like for example, some of this dark red area now is what used to be higher. Now it's in the medium low. So it went. Sorry. Okay. So it went from 0.9 to 2.5 kilograms to 0.5 to 0.7 by adapting the filter strip. Next we did the, remember it's only 50% of the land is converted, not all the land. And next we put the filter structure so that we can reduce the velocity along the river. Okay? We put structure so that the flow in the river is not going to be very fast moving. So we put this boulders and things like that to stabilize the river. Okay? So that reduced a little bit, actually not significant, it's only 2% it's going to reduce. Then we put grass. This is the river, so we put grass in the entire river actually so that we can reduce again the velocity in the river. Okay? So that helped a little bit. I mean, you can see the changes. So you can see the color changing on the map, what's the basin. And this is the grade stabilization structure. That means you are putting, sorry, this is the terraces. So you are putting terrace for the slope protection. Okay? And then the biggest benefit is conversion to the pasture. So you can see there is a significant jump from here to here. Okay? So we are taking 20% of the agricultural land and converting them into grassland or pasture land. Okay? And then finally we put prescribed grazing, meaning allowing the number of animals per hectare in the land. So you don't want to overgraze. So with all these reductions, now you can see most of the phosphorus is under control actually, less than 0.3 grams per hectare. Okay, so we had two different grazing scenarios, and we also put a buffer. This buffer, 2,000 feet buffer, is just around the lake to protect the lake, not the landscape, but just the lake protection. Yes.
The filter strips do simulate with forest.
Yeah, you can do it forest, but forest does not produce that much water quality problem. Yeah, there's not much water quality problem. It's an agricultural land and the grassland is the maximum. So, yeah.
By conversion to pasture implies like economic change, like agriculture for
Yes.
cattle.
Yes. Because this area is rapidly converting to urban because of the Dallas area is approaching actually. So what we are saying is, instead of going to urban, it's better to go to grassland. If you do more urban, then means more parking lot, more rooftops, that means more runoff. Okay, so you're going to have more erosion, more nutrients and things like that. Yeah. The land has to be managed better by converting into grassland. I mean, that's the last slide on that particular topic actually. So just that gives you a rough idea how a model like SWAT can be used in combination with stakeholder, farmers, and also working with economists to figure out the optimal way to reduce the load going into the lake. Because you cannot build a lake, it takes almost 70 years to build one lake in Texas now, because of the environmental laws. It's not easy to build a lake. Okay. I'm working with the same group to build a lake for 30 years. We are still in the drawing. We have not even done anything beyond that. That's how difficult it is to build a lake. So protecting an existing lake is more important, more economical than building a new lake. Okay. Because the population is continuing to increase. Right now, the state of Texas, the population has gone up from 22 million to 30 million in the last 30 years. And they're expecting that to even double in the next 50 to 70 years. So that means we need more water. So that's what this is all about. Economics on the large scale. So just to conclude, we have more than about 10,000 SWAT users worldwide with 30 active developers. And we have about 8,000 masters and PhD students and more than 6,000 peer-reviewed publications. Every year we are publishing 650 peer-reviewed papers per year. Okay. I'm talking about the world community, not me and my group, the world community. Okay. So we do conduct several annual meetings, and we are planning on one meeting next year in Lima, in Peru. Okay. So I'm hoping some of you can participate in that conference also. Okay. That's my last slide on this one. So this is again another paper where we looked at the blue gold rush. Actually, we know 100 years ago it used to be yellow gold, right? Everybody wanted the gold as a metal. Then there was a black gold, which is the oil. Everybody was going after oil under the ground. And now what we predict in the future, it's going to be blue gold. Blue gold is nothing but water, renewable water. Okay, we talked about the virtual water trade, right? That's the blue gold. Okay. So yeah, we looked at transboundary water issues on one of the largest wetland in the world called Al-Hawaiian marshland in Iraq. Okay. This is purely a man-made problem. Okay. This is not natural disaster or anything. This is all human-induced problem. Okay. So we analyze this using the SWAT model to highlight what's happening in the Al-Hawaiian marshland. Just to give you a perspective, this is a heat map produced by UNEP, United Nations. Each circle represents the amount of conflict, water conflict in the transboundary between different countries. The larger the number of circles, almost 40, 60, 50 different conflicts. So you can see most of the conflicts is in the Middle East area. Okay, that's where there's not enough water because it's extremely dry desert, and that's where most of the problems. We also have problems. It's not only the transboundary means it's not between country to country, it's only between state to state.
Yep.
Okay, so in the U.S. there's a lot of territorial water issues between different states. Okay.
We have this in Brazil.
You do?
Yeah. São Paulo, Rio de Janeiro e Minas Gerais. E Paraíba do Sul, River.
Yeah.
What's the meaning of the colors?
The colors is how the river basins. Actually. These are the river basins.
Okay.
Oh no. Sorry. Okay. So the color here represents the circle represents the number of conflicts. The color represents the period 1980 to 2005. During that kind of number of like a war, if you want to call it actually, dispute. I think this slide will give you a better thing. Actually. In the world, as of today, there are about 1,300 conflicts. These are all, each dot represents a conflict. Okay, that means a war or something like that, a dispute is going on actually. That's for the last 100 years. But if you look at the last 30 years actually, 2010 to 2019, there is about 829 conflicts. In the last 3 years, we have 202 conflicts. So always the Middle East is the hotspot of this conflict. Okay. So you can look at this website called Water Conflict Chronology to see where are the conflicts and what conflicts and things like that. And this is another, just to show you the Tigris River. This is what I'm going to talk about. And then there is the Aral Sea and the Nile River Basin. They are constantly in tension between the countries. Okay? These are all the other areas that has got potential. They are not there yet, but they can be any time. Okay? So the yellow is potential, and the red is already in deep conflicts. Again, the same slide what I showed you of the virtual water trade is one of the reasons why we are having this problem. Okay? So again, I don't want to go through this. I just want to, because this presentation was just another group actually. So I had the blue and green water analysis. And the SWAT. This is the main presentation I want to get into. The hydrology of the Tigris River and the tributaries contributing to the Al Hawaii marshland. So where is this marshland is located? So this is Turkey. This is the Tigris River Basin. The region 1 is all Turkey. Region 2 is up to Baghdad, okay, in Iran. And then region 3 is from Baghdad to the Gulf. Okay. So you can see the solid yellow means there is a dam already exists. The light yellow means they are proposed new dams. Okay. This is a schematic diagram of how intensively managed water resources. There's nothing natural here. Everything is impacted by human. This area is completely hilly area. 95% of the water in the river is produced here. Okay, these are all desert. The average rainfall is less than 200 millimeters. Okay. So 95% of the water is coming from Turkey. And if you look at the Turkey, right now they are building a huge dam. The entire world opposed it, but they went ahead and did it anyway. At one point, the Germans were funding that project, and because of the world pressure, Germans withdrew the money, but still the Turkey went ahead and built the dam. This dam can hold the entire 1 year of all the water that it can produce. That's such a huge dam.
That's a regional conflict.
Yeah, regional conflict.
Up there.
Yeah.
You're talking about the technical issues, and also there are other
political
people. Yeah.
Yeah.
You take into account.
Yeah. But luckily, the Turkey cannot have agricultural operations because the land is not suitable for agriculture. It's mostly hilly area. So it's made for the energy production. They can't hold the water, but they have to release the water downstream, because they are not using the water area. Unless otherwise they do transfer from here by pipeline to other parts of the Turkey. They have not started that yet, but still already we have a lot of problems. Okay. So, oops, sorry. So that's the schematic diagram of all the water coming into the Tigris. This is the main Tigris River, and these are all the tributaries and the dams that control that. Okay. So right at the border, Turkey to Iran. Okay. So this is the next section from here to here, from Turkey border to Baghdad. And again, you can see all the dams. These are all existing dams, and this is all proposed new dams. Okay, and they built a huge lake in nowhere. Actually, it's in the middle of desert. They created a lake, artificial lake, to transfer water from Tigris River by pipeline and then putting it over here. In order for them to irrigate the Mesopotamian basin, we know the civilization all started from the Mesopotamians for all the agricultural activities. That's where this water going from here.
Lots of evaporation.
Lot of evaporation. Almost 1 meter of water is evaporated every year. I'm going
Is
to
that a
talk
good decision? Is that a good decision?
But I mean, this is how they've been doing agriculture for tens of thousands of years. But those days there is no dam. Water was freely flowing. They were just using that water. So now with all the dams constructed, there's little water. That's what I'm going to talk about.
What's the age of the lake?
Age of the lake would have been at least in thousands of years. Yeah. They've been doing this more than thousands of years in civilization. Okay, and this is the lower zone, the third zone here actually. So below Baghdad, all the way to the Gulf. And this is the Al-Hawaiian marshland. This is the largest wetland in the world, 4,000 square kilometers. Okay? It's very shallow. You can walk literally. It's only 1 meter deep. Average depth is 1 meter only. But it is 30 times saltier than seawater. Okay? It's highly salty. So there are 300,000 people live on this marshland. It's a floating village. People live on the water basically. Okay? So the importance of this marshland is very significant. And the marshland is shared by Iran. Part of the marshland. So this line that you see here, this side is Iran and this side is Iraq. Okay? There's a lot of geopolitical issues with this. So we were asked to look at the historical perspective of this marshland and what is happening here actually. So we divided the lake. This is the marshland. This is a satellite image. We divided that into 4: Iraq, Iran, upper and lower. So this gives you a rough breakdown of the amount of area that's available at that time actually. And we used the 250 meter 16-day composite MODIS imagery from 2003 to 2013 to analyze how much water, how much vegetation, how much is the background for the time period. Okay. So this gives you an idea for the upper quadrant, where is the land, where is the water. And this period was extremely a dry period actually. Even after the dry period, you had some water in the upper Iraq. But if you look at the lower Iraq, this is completely gone. There is no water at all. Okay? And this is the upper Iran. Again, during the drought period, the water is very, very low, and the water is completely gone. So this just gives you a rough idea of the animation of the water. So the blue is the water, the green is the vegetation, and the brown is the open land in that period actually. So we created this animation for week by week for 20 years of satellite data. Okay. So this is what used to be. When Saddam Hussein was running Iraq, they had 4,000 square kilometers actually. 1973. 1990 is when the war broke actually. Okay? It still had sizable wetland. That wetland is now reduced by 33% in 2000, 62% in 2004 because of the flood, and then again it's reduced back to 33%. Right now it's only a very small portion. Okay? 1/3 is what's available. Okay? Even that 1/3 is not continuous area. It's broken. So previously when people were able to move by boat from one to another, now they cannot move. Okay, these are all local packets. Okay? It's not contiguous area. So this is how they were living before actually. These are all like a village, like a group of families living together on the floating. Okay? So they had even education in there actually. So people can go to the school in the floating village area. So this is a very, very salty land. They cut the grass to feed to the animals. Okay? And fish is the major production here actually. So this is how they were, so this is after they removed it, now it's all small patch of land actually. There's no, you don't have any more boat to go around in that area. Okay? So this is where they stand today actually in terms of what's available in the region. So we use the SWAT model to analyze the 80s, 90s and 2000s on how this has changed over the years. Okay? So that's what I'm showing you here. Okay? In the 1980s, this is how much water was available. There's plenty of water to take care of the 4,000 square kilometer marshland. In the 1990s, because of the dam, because of the war, because of the conflict and everything, that is starting to reduce. This is the probability of exceedance curve. This shows you 100%. Okay. And in 2000s, even further reduced because in 2000, exactly 2003 or 4, Iran built a dam in Korhe River that is 3 times the capacity of the annual flow. In other words, they can hold water for 3 years and not release any water to this marshland. Remember, part of the marshland supply is coming from the Iran side. Okay. And in 2007, they went and built a wall in the marshland so that people cannot go back and forth. Because as the marshland started to shrink, people were starting to go into Iran. So they started building a wall. So the water cannot come in, people cannot move around, all those problems, all the geopolitical problems.
How is it now, 13 years later?
It is still the same problem. Right now, one of the biggest income for them is the tourism, ecotourism. So there are a lot of Europeans go there and visit these villages actually, and they make more money from the tourism than the fish that they used to produce before.
That puts more pressure.
Yeah, because there's not enough thing for them to, there's not a hotel for example. Okay, you have to travel almost 3 hours to go to this place, watch it, and then you have to go back, so you can't just live there. And this is what used to be the flow in the Iran side. After they built the dam, it's almost completely gone. Okay. So don't worry about this low and high, just concentrate on this one. Average flow in 1980s from the Tigris River. This is the border between Turkey and Iran. We used to get about 27,000 million cubic feet of water on an average. By the time it comes to Baghdad, it's almost 42,000, even after taking the water to the lake. Okay, 42,000. And the amount of water that goes into the Al-Hawaiian marshland is almost 40,000. What you need is only 5,000 million cubic feet of water to maintain the Al-Hawaiian marsh of 4,000 square kilometers. Only 5,000 is what you need. So what you get is almost 40,000, 47,000 back. So you have plenty of water in the 80s. When we moved to 1990s, this is what happened. More dams were built, more conflict. So now that went from 40,000 to 19,000 at the border between Turkey and Iraq. And by the time it comes to Baghdad, from 45,000, now it's become 22,000. And now it's got less than 18,000 when it comes to below Baghdad, for example. Then in 2000s, it's now significantly reduced to 9,000. What used to be 22,000 now is only 9,000 million cubic feet of water. And by the time it comes to the Baghdad, it's only about 10,000 now. What used to be 47,000, now it's only 10,000 million cubic feet of water. And it has significantly impacted what's happening in the field. So again, I'm just showing you the lower portion, the third segment I showed you before, in the 80s, in the 90s, and in the 2000s. So what used to be almost about 15,000 is reduced to 10,000, now it's reduced to 3,000. What you need is 5,000 in order to maintain. Okay. And this 3,000 is not consistent because what's coming from Iran, they can stop it any time for 3 years. And you don't have enough water in the market. Okay. So this gives you a rough idea what is required. And in the 80s, we were able to maintain 100% of the time. In the 90s, we were able to maintain almost about 80% of the time. In 2000, now we are able to maintain only about 40% of the time. The amount of water required to maintain the alkaline marshland. Okay? So this is all based on the existing conditions, right? Then let's talk about the future, because there are still more dams to be built. They are not finished with the building the dams. Okay? So this is the current dam, how much inflow and how much volume. So right now they are storing almost 48,000 million cubic meters of water in all the dams, storage. Okay? And how much they are evaporating? Almost 3,500 of them is evaporating. What is required is 5,000 million for this marshland. They are evaporating almost the same amount of water that's needed for the particular alkaline marshland. This is based on existing, right? If you add all the new dams, these are all the new dams that's proposed. Some of them are under construction. They are going to add another 27,000 more storage. Already there is 47,000 or 48,000. They are adding another about 28,000. If they add all the 28,000, our expectation is that we are going to further reduce the amount of water available to the alkaline marshland from 33% where we are today. It may go down to 10 or 15%. So that's the major challenge right now is the impact of all the dams and all the water diversions and all the conflicts that we have between Turkey and Iran and Iraq, all those stuff is going to make even more worse. There is no strong central government system or federal government system that looks at the entire system. Everybody is looking at the region because right now, because of the conflict, there is no central government or federal government that looks at this problem holistically. It's not only Iraq, it's one, most of the countries, the same thing. Even in the US, the federal government does not own the water. The water rights is state. So state can do anything actually. If you are an upstream, if you want to block the water, you can block it actually. Okay, so that's why all these international conflicts are coming because water is not a national resource, it is a local resource. Whereas oil is a national resource. So we should be thinking in those terms actually, holistically, water as a national resource, not as a local resource. It should be shared with everybody, not just the regional area. Does that make sense? So this is where we are right now with current and with pre and post dams actually. This is before the dam. And this is after the dam. The expectation is this is going to reduce by even another 50% than where we are right now. Okay. That's